Hello friends, welcome to the fourth video lecture of the series, and in this lecture we are going to discuss few problems. So our first problem of free body diagram is shown, and if you remember I used this problem as an example while explaining you the equilibrium concept. So to start with this problem, let's recall reaction forces. Yeah, so the external loads that are applied to a member must generally be transmitted to the adjacent members that are connected to the given member or carried directly to some form of support. So, for explaining this, let's take an example. Here, in this example, a frame is subjected to loading at different conditions, at different locations. So, the loading to which the frame is subjected are called external loadings. And these external loads will be balanced by the reaction loadings that are generated at supports such that the equilibrium conditions are satisfied. So as you can see in this figure that mm, the forces that are shown in the blue color, these are the external loadings that you are providing, that you are applying to this frame, and because of these loadings the internal reactions are generated, the arrows that are shown in brown color. Okay, so what you can conclude is, like in the study of mechanics of deformable bodies, we consider not only external forces and couples like the applied loads and reactions, but we also must consider the internal resistance, that is the forces and couples that are internal to the original body. So let's take an example of an L frame. Yeah. A frame is subjected to the end force and it is pin joint at one end. So here the frame is subjected to the loading. Let's call this loading as P. Yeah, I'm denoting it as P. Okay. So when you will resolve these forces, what will come here? This force will be this angle with the horizontal is theta. So this component will be P sine theta. For theta, I'm using the asterisk sign here. And this will be, okay, this is P sine theta. And this will be P cos theta. Okay. Yeah. And here the end point here, this is the end point and this is the pin joint. Now like pin joint can't resist movement, so first thing to investigate is that the applied loading produces movement or not at the end point. From our previous lecture we know that a pin joint will constrain translation motion so that there will be reaction in horizontal and vertical directions. So let's call these reactions as Rx and Ry and take it as a positive as along the positive x-axis and along the positive y-axis. Now we'll apply the equilibrium conditions to find the reactions and verify that the moment about pin joint is 0. Okay, so the reaction that I've shown here is Rx and Ry. Now apply the equilibrium conditions, that is the summation of forces in x direction is 0, summation of forces in y direction is 0, and summation of movement at any point is equals to 0. So first when you'll apply the when you'll do the force balance, what you'll get is P cos theta is equals to Rx. Here let me show you this thing. P cos theta is acting in this direction, right? And Rx is acting in this direction from what we have assumed. Okay, if in the end you are getting answer in the negative form, that means that whatever direction you have assumed is incorrect and we'll just reverse the directions. So when you will do the force balance here, what you'll write is P cos theta plus P cos theta minus Rx, since they are in opposite direction, is equals to 0. So P cos theta is equals to Rx. Similarly, P sin theta is this component is acting upwards, and similarly according to what I have assumed is Y is also acting upwards. So P sine theta plus Ry is equals to 0. So from this equation what you will get is Ry is equals to minus of P sine theta. That means the direction of Ry we will reverse in the end because we are getting negative in our answer. Okay. Now moving forward and applying the moment equilibrium conditions. Now the perpendicular lengths are L and H respectively. So when you will apply the moment to the pin joint, what you will get is P sine theta multiplied by L plus P cos theta multiplied by H is equals to 0. Since you can see that P sine theta and P sine theta is producing a clockwise movement about our pinpoint, and P cos theta is producing anti-clockwise movement. This is the reason why P sine theta is carrying a negative sign and P cos theta is carrying a positive sign. It is not any hard and fast rule that you have to take clockwise as positive or anti-clockwise as negative. It is simply like if you are taking one as positive, the other will be automatically negative. Okay, so taking cos theta common, what you will get is minus P tan theta into L plus P into H is equals to 0. Now you know from the trigonometry that cos theta can't be equals to the 0, can't be equals to 0. So our inner bracket will be equals to 0. Now from the diagram what you will get is tan theta is equals to H by L. Substituting this value, when you solve this, what you will get is 0 is equals to 0. So what is the conclusion? It concludes that at the pinpoint there is no movement. Okay, so moving forward, yeah, now we have already found the reactions. So now let's investigate like how forces are developed internally in the structure. So if you cut a structure about a line AA and you'll use the equilibrium balance for each section, what you'll get is something like this. See, what is important here is at each cut section, your equilibrium conditions must be satisfied. So when I'm taking an AA plane, equal and opposite forces and equal and opposite movements are produced on the both ends. So unless and until you will not applying any external load at each cut section, your whenever you'll take a cut section, it will automatically be in the equilibrium condition. Okay. So moving forward, what is the summary? Like what you can conclude from this numerical, from this problem that we solved. So for solving any problem, any numerical related to the free body diagram, first you need to determine and isolate the body. Just completely isolate the body from its support and from any other body that is attached to it. When external resultants are to be determined, pass a sectioning plane through the member at the desired location. That's it. Sketch the outline of the resulting free body diagram. Then indicate the external loads. Just show whatever the external loads are provided in the numerical as an input. Just indicate all these external loads. Then show the unknown forces and couples that are exerted on the body by the adjacent bodies. And then finally keep the free body diagram as simple as possible so that it conveys the essential equilibrium information quickly and clearly. And this last point that I'm going to show this point from using our next example. So in this example, I'm taking this is an example of a truss. This problem is kind of a simple looking problem, but it is not actually simple. It will teach you a very important way of handling problems. So just take a moment to think what we can extract from the problem statement. Well, what is given here is weight of the sign bolt is 400 Newton, and what they're asking is find the internal forces in Fg. Okay, so given is the weight of this Videopedia sign is given as 400 Newtons and the internal forces in Fg. Okay, now think that what will happen because of this weight. See, if you analyze this, you know that weight of the sign bolt will tend to pull the truss away from the wall at A, joint A, and forcing the wall to push the joint at right, forcing the wall to push to the right at the joint G. So therefore members along the top of the truss will be in tension, and similarly what about the members along the bottom? They will be in compression. So now you know how this truss is going to behave. Now you know what are the input conditions and what is our main aim in the end, like we want to find the internal force in Fg. So now we'll use the method of section here to find our internal force in Fg. So for our first point, that first we'll pass a sectioning plane. So what I'm doing is, first I'm passing along XX, okay, and after that I'll pass one more plane. So first time when I'm passing this sectional plane XX, what are the forces that I'm getting? I'm getting this F3, because as this XX is cutting FG, FB and BC, so I'm getting three forces, F3, F4 and F5, as you can see in this question here. Similarly, when I'm passing the sectional plane YY, what forces I'm getting? It's F1 and F2, correct? Now you know that weight of this block, the Videopedia block, is known. So what is the first thing that you can do using that your information, whatever you have? You can find F1 and F2, right? So weight of this block is 400 of it, yeah, 500. So what will be F1 and F2? As you can see, it's a symmetric distribution. So F1 and F2 is equals to 500 divided by 2, simply 250 newtons. Now you know F1, now you know F2. So what you will do, again you will use the equilibrium conditions and you will find F3, F4 and F5. But if you remember that what I've told you is, you should not always go in the same direction. Obviously conventional approaches are very beneficial, they always give you a solution, but for this case what you can see from this numerical is that F4 and F5 are passing through a single point. And what does it mean? That means that they will not generate movement about that point. Now from moment equilibrium, we know that for static equilibrium the sum of movement about any point must be 0. See, we are talking about any point, okay, and this is important. So if you are going to take force, if you're going to take moment balance about point B, that is a blue dot, it's shown here, we don't have to do the force balance because there is one unknown and one equation. And this is the main reason for choosing this problem. Now before solving the problem, we need to fix the sign convention. So what I'm going to choose is, I'm just choosing clockwise to be positive and anti-clockwise to be negative. And after solving, if we get a negative sign, so what does it mean? It just says that the assumed direction of force is reverse, and we have assumed the tensile force as positive. So the actual force in the link will be compressive. Okay. So I think now I have explained the problem, and we can proceed. Yeah. The summation of moments at point is equals to 0. Now just apply the moment summation along the blue, for the blue dot. What you will get is F1 into 1.2 plus F2 into 2.4 plus F3 into 1.8 is equals to 0. See, if you have noted down the distances, I'll mention them again. Yeah, this distance was 1.2. Okay, this distance was 1.2. Again, this distance was 1.2. So for F2 it is totally 2.4, and for F1 it is totally 1.2. Okay. So some arrows are not proper, but it's okay. Similarly, this distance was 0.9, 0.9, 0.9, which together will make for F3, this total distance is 1.8. Okay, I think you know that we consider perpendicular distances here. Now check the direction. F3 is producing a clockwise movement. Similarly, F1 is producing a clockwise movement and F2 is producing a clockwise movement, and this is the reason why this equation is very simple, because all these moments are having the same sign. So when you solve this, what you will get is, you will get F3 is equals to minus of 500. So that means that what direction we assumed, and what is we need to reverse the directions in the end. Okay, so using this simple trick, what we did is we solved this numerical in a very simple and in just like in 2 minutes. If you're going to do this force balance one by one and like that, then also you'll get this answer. But remember the last point that I've told in that is you need to inspect the problem. You need to inspect each and every problem, and you need to think, okay, how it is going to behave, how our forces are behaving in that, and so you can solve the problems like this. Don't worry, we'll cover some more problems in our subsequent lectures. So thank you, and if you like the video, please subscribe for more interesting videos.